So this is so the last systematic action, right? And this is a bit different. So it's a lecture. It's about sequence generation, and in a way, that is the core engine. So this, in a way, is kind of interesting. It's the last thing we do in the book. That this space is also the last chapter. There's an appendix kind of chapter, but the last main chapter. Even though it's the core of our theory, and it's core in the sense that this whole approach is is emphasizing that most activity that supports thinking and acting is self-generated, right? It's generated inside the nervous system. It's not just transducing input into outputs. Unlike the classical thinking, most of information processing thinking, but also some connections thinking, is emphasizing that you give some stimulus to get a response. A lot of work is like that. And we emphasize, no, it's largely self-generated. You can actually minimize sense information, close your eyes, plug your ears and still think and act. And so far, this mostly took the role of, or the form of keeping activation around. So sometimes there was activation from previous inputs, and you had some peak somewhere, and you could keep those. That was when it was working memory. And then we talked about how you could have some inputs, but they're not very specific. Like you can just get a cue, and then by cued recall, you can bring some activity to be super threshold that was, reflects memory then, and can do things like that. But in a lot of these higher cognitions things, we already have sequences, right? I just explained how it works, but we already saw that when you actually think and act, you do more than one stable state, right? You're going through different stages. So I'm arguing here that all behavior and thinking essentially consists of sequences of mental acts, of mental states. It's very intuitive, introspectively, that your thinking consists of that. When I'm speaking like this, right, I'm saying one word after another, one phrase after another, one gesture after another, orient to one object after another. And that is all generated from within me, right? Not triggered by some external stimulus. So in that sense, sequences are the basis of everything. You can see how central that is. And one could say that what dynamical field theory is about providing the tools to provide a neural account for that. That is, the tools for how neural activation can arise in forms other than triggered by inputs. And you already know some of that, but how systematically this is now done is what we'll do understand today. So for that, it's very important to be specific about what kind of sequences. And you could think, again, maybe of two things. You could think, well, there are fixed sequences that you've learned, particular patterns, like you can make a move and reach, grasp, lift, and so on. And that's something that you've done many, many times, fixed in some sense, right? You will all first open your hand and then touch the object, and then you close your hand. No way that you're going to do in some other order, right? But some natural fixed sequence of that. And that would be a fixed sequence pattern, but it's still autonomously generated potentially. But we can also make fresh sequences all the time, right? And hopefully when I'm speaking, I gave this lecture before, but I'm not actually following exactly the same steps. So certainly the details of my train of thought are not totally fixed. No, as you get older, supposedly you're more and more doing the same thing again, but it's actually not entirely true. And of course, a lot of your actions in daily life consist of new sequences every time. Maybe it's most explicit when you solve problems, right? Then supposedly you find a new solution, meaning the first time you find the right sequence of events to do something. And there's some computer games actually that exactly bring you to that point to do that, supposedly, right? So in that sense, you see that sequences are really foundational. A little bit hard to put your finger around that, and that's why it comes so late. We need a lot of machinery to do that right. So this is, by the very nature of this, a very broad topic. So if you look into textbooks in psychology and neuroscience, you will find only very special cases being discussed, because those are the cases that you can study easily in the laboratory or have some neural data about, even though it is so pervasive. And you will find, for instance, that cognitive process, for instance, about memory or about decision making that involve sequences, but they don't really discuss that sequence aspect very much in there. They separate it out, and that's sort of, just because of this need to focus on that aspect as such in your defined paradigms. So the most famous variant of looking at that is serial order. So that is essentially paying attention to the ordinal, the order of things, so the ordinal dimension, how things are ordered. So for instance, phone numbers are all have the same contents. They all contain numbers from 0 to 9. And the only thing that makes them different is the order of these numbers, right? Of course, maybe also which numbers appear. So you see the two aspects now: which numbers appear in a phone number, and in which order do they appear. And you can, for instance, really remember that to some extent, right? And so when you're remembering that, you're not just remembering which numbers appear there. In fact, you would be probably hard put to say that a priori which numbers appear in your phone number. The only way you would do that is actually recall the phone number and then check which numbers are in there. But you're certainly sensitive to the serial order. And that actually is maybe the first instance of people really becoming very aware of this ordering problem. There's a famous physiologist, Kurt Lashley, who studied this in the 1920s, I believe. So he will always be cited there. And so his special claim to fame is to have discovered through neuropsychological means that the ordering is sort of a separate thing from knowing the contents. This what he did was study people with lesions. It's literally First World War, gunshot wounds, lots of gunshot wounds. Lots of people had brain lesions, survived. These guns weren't as powerful as today's guns, so often with a headshot you might survive. I don't know. But they had a lot of patients. And so neuropsychology was essentially bootstrapped by that. There's a lot of description of what kind of deficits people had when they had these localized lesions as a consequence of gunshot wounds. And so Lashley found a sizable set of people who had selectively a difficulty of remembering the ordering of items, while their performance on which items were in the sequence was at least, maybe not normal, but was affected less. So there must be some specific substrate, neural substrate, that is responsible for the serial ordering. That's where this idea came about. And there's a lot of other ways of assessing that in the meantime by behavioral study. So this is a much larger literature that I can talk about, and there are some scale up. You can scale that up from this very simple material. I don't want to go too deep into that. And so the one variant is that learning the ordering of things is sort of automatic. So when you will even it's sometimes called implicit learning, that is, if certain things tend to repeat, you will pick that up. And it's a famous example of that is people doing something like tracking. So, for instance, with a pen, tracking on old-fashioned instrument with a pen on a rotating bar, they track something that feels random, and it turns out there's only one piece that is somewhat reproducible, that has a similar sequence of events, of turning points, and people can't really tell which that piece is if you do that right. But then when you look at their performance, they're better in that piece. So they have learned something about that. So in that tradition, it's really ordinal, and that is actually the majority view, that you think of that as ordinal. And a lot of these activities happen somewhat rhythmically. I mentioned before that speech actually is also somewhat rhythmic, as a sort of periodicity to speech. And one way to see that is that you can actually entrain speech with a metronome. You can speak in a particular rhythm. Sometimes people do that. Like in singing, you do that all the time, right? Which is kind of interesting where that comes from. So ultimately, the material from which speech articulatory movement is made is the same kind of material from which other movements are made, and they do have a timing. That is, they have the property of arriving in time at the right moment in time, as you do when you catch and so on. So those of you who took my summer course, and I'm not sure anybody is here, or will take my course in the summer where I talk about timing of movement a lot, and that overlaps here. So in sequence generation, and especially when you talk about it really in this form of serial order, people don't really think about the timing. And in practice, it's often somewhat rhythmical. When you record a phone number, you take often the same amount of time to recall the next number, for instance. But a lot of real-world sequences and also incremental sequences are not like that. That is, they might be of the nature where one task takes a little longer, and then you're going over to the next task. Let's say, for instance, coffee making, where you would have a certain, depending on what kind of machine, like one where you fill the filter, like you put the water in and so on. So you have a certain sequence. Like you can't start to put the coffee into the filter before you put the paper filter in. I'm not sure if these kind of ancient systems still around, but that's how you used to do it. So there is a serial order, but there's also a timing issue because some things are very quick and other things take longer, right? And you will not go switch to the next action just because time is up. Really finish that. For instance, if you're held up because something, like the paper filter didn't quite fit, and you have to do something extra to make it fit, then you're waiting until you're done to activate the next one. That's an aspect that we'll be looking at, because when you act, then that happens very naturally, that there's different amounts of time, and that you actually can keep the serial order intact, even though you're perturbed, for instance, kept from doing something. This is actually also a case where you can see that it is it's an achievement in the sense of the brain to do that. So for instance, one of the well-known problems of people who have frontal brain damage is that they sometimes cannot keep that serial order intact. So from the frontal brain is very much the part of the brain that is responsible for goal orientation, for focusing on tasks, cognitive control, and so on. And frontal brain patients have sometimes trouble with that. So that means concretely that if there is a very inviting stimulus, and the stimulus invites some other task, they might switch out of the task and just do that. And famously, some of these patients just go through an open door because the door invites to go open. They were on their way somewhere else, but it also kind of attracts them and they go through that. And so one manifestation is that what is called perseveration, that is, they get stuck in a particular phase. There are some movies, I mean, this is neuropsychology, it's very individual, it's sort of just qualitative. But there's some clips where you have a patient like that making coffee, sometimes used in the lab as a kind of a daily life task. And then you can see this person puts too much coffee into the filter and even says, oh, maybe this is a bit too much, but it gets stuck on this stage and it overflows and kind of trouble to switch to the next one. You also see that sometimes children can get sort of stuck in a subtask. There will be a problem of the timing of the action, of finishing correct. So of course, a lot more can be said about that, and it's very diffuse and broad. But I'll switch now to really think about it in our neurodynamic terms. Now, in our particular emphasis, we argued that you need attractors, so stability as a prerequisite. It's one of the ideas when the neural activation is not generated just by input, but it is internally generated, then you need to keep it there. Sustained activation would be really the formal case of that, where you keep activation stable after you have reduced the inducing input. So that's stability means resistance to change. But when you're talking about a sequence, that entails change, right? It means go from one to the next. So you see that there is a inherent conflict between this view of something as a sequence compared to something as an attractor. And the answer will be, what you have to do is you have to make the previous state unstable. And then you can switch to the next state. And in fact, that's how I'll organize the lecture. I will now first talk about that. We call that the condition of satisfaction. You will see in a moment why that makes sense. And that's always about ending a state in a meaningful way. And then I will talk about how you then actually select the next state. In the first case, I'll show you a couple of models that also then select the next state. But then I'll show you more generally how the next state, what the general ideas are about how the next state might become active. And this, already you can see this maybe has to do with this, what I hinted at the timing, that you want to make the previous state unstable at a under well-defined conditions. So for instance, when you're done, and not just because a certain amount of time elapsed, even though you could also do it periodically, perhaps. Good. Here I'll first explain that around our historical example. That's the example around which we developed a lot of the math, and then I'll tell you the more abstract thing. So this is it was actually the doctoral thesis of Julia Sandomierska. She's cited here at the bottom. This is the paper from 2010 that was the foundation of that. So I'll first explain maybe that task. So we thought about this for hard, and this is a really well designed task. It was done on a robot, but later I'll show you the different versions of doing it. And this was really just to act it out, show that you can actually act it out, but you can also purely do this purely mentally if you want. So the robot was had a serial order task. The robot learned that it should first go toward a blue object, then toward a red object, missing the number 3 here, then toward a green object, let's say, arbitrarily. And in practice, you'll see in the moment, the robot is actually just a little vehicle, and it doesn't really know where things are. So it just walks around by opposite avoidance, and thus it takes it just randomly will find it ultimately. And so it takes different amounts of time to find these objects. And that was the idea, that we look at exactly that it, in other words, keeps in mind, I'm looking for a red one currently. And it does that until it's done, until it's found the red one. And in particular, it might actually run into the green one as it is looking for the red one, but we don't want it to now switch to the green one because it's also in its table of future goals, so that it can really keep the current intention stable until it does the next thing. That was the idea. So here's an example of how that was done. We actually taught the sequence. Let's first assume the sequence was known. So you've learned that yellow, red, green, blue, and red sequence, and then the robot just roams around an arena where these different objects. It simply avoids objects. Once it's seen an object of the suitable color, it actually will move toward that object. So for instance, I think soon one of those, maybe it is not this one. I think it's maybe moving toward this one. Don't remember exactly. Or is it this one? Yeah, this might be one that it really moved toward, and then it moved away from that. And here, for instance, it ignores this one. And I think it's going to some other one. And as soon as it finds an object of the right color, it actually moves toward that. And you will see that the way we designed that is that it moves until this object is large on its visual array. And then that tells the robot it's done. The order in which the order of color was actually taught. We showed the robot objects of different colors in a particular order. And actually, every presentation was ended by moving the object a little closer to the robot. And then when it was large, then the robot switches, okay, now I have learned this one, show me the next one. So this learning sequence also didn't have to be periodically timed, even though it's natural as a human that you kind of do it rhythmically, but it wasn't precisely done. And I think I have slides here, yeah. This is where the robot moves to the red, but at that moment in time, red is not its goal. Its goal is something else, something that I don't know where it's going. You see sort of driving by that. While in this case, it's actually going for the red as its object. It's really going there and then turning away, right? And that's sort of what we're aiming at. The system is able to keep in mind its current goal, that's stable, and ignore distractors, which would be possible goals that are not currently the goal. Good. And so this is the architecture that we used for that. Actually, we had multiple different variants of that, and I'm going to mix the variants because I have a very nice video from one variant, and the other one is easier to explain. So here at the bottom of that architecture is stuff that you're familiar with, and I'll illustrate that again. Essentially, there's visual search here at the bottom. It's just done here by the robot moving around rather than by just in the visual array. And the important idea is that we have an intention field. That is, the robot has a goal. We call this an intention. It would be a motor kind of an action intention in terms of Searle's intentionally, a world to mind directional fit intention. we're also dealing with the opposite kind of intentions in some of our work. And so, for instance, here it's defined by color. We took coloring because that's easy for our sensors to pick up. And so it's you put a peak here in a field defined of a hue that reflects which color I'm currently looking for. For instance, currently I'm looking for green, let's say. And that intention controls ultimately the robot's behavior. It does that actually in the way that you might be familiar with. It puts a ridge into color space fields. So the color space field is fed from the visual array. It's actually just one-dimensional space because the robot just looks horizontally. Everything is sort of summed. Anything in the visual array is just in terms of its heading direction or horizontally. So one dimension is the horizontal space, like the circular view. It's only about plus minus 100, I think 120 or something, how broad that camera is. And the other is the hue dimension. And so where that ridge overlaps, you will get a peak. So that's how it finds a peak. And then once it has found a peak, it will use some robotic neural dynamics actually that I spent summer semester, how it actually moves toward that object. So that's sort of how it's looking for a color. And the finishing that behavior, the termination of a stage like that is done by what we call the condition of satisfaction. Now, some of you might know the concept of intentionality from philosophy. Some of you are philosophers or in cognitive science, you're exposed to that a lot. You might know John Searle, some of you, consciousness and so on. So he pushed this idea of intentionality one step further, and he analyzed its structure in more detail, and he proposed this concept of condition of satisfaction. So when you have an intention, then its condition of satisfaction defines literally what it means. It defines under which conditions that intention is satisfied. There's a difference between world to mind and mind to world conditions of satisfaction, or directions of it, concept and conditions of satisfaction. The normal intention that we talk about is the world to mind, that is you're trying to achieve something in the world, is like an action, action intention. I intend to lift my arm, so was the example in Searle's book. So intend to lift my arm, and the condition of satisfaction that it is up there, and that it is up there because I actually caused that to be. And that's from him the logical condition of satisfaction. Now, what it means to logically achieve that intention, while we'll make it a process element. That is, we'll control the sequence of events through detecting that logical condition. For the other kinds of intentions are what you would typically call something like perceptions or memories, where your mind has a state that matches something out in the world. So it's you achieve that your mind does something that you have out in your world. So like if I look at one of you and I have a peak of activation somewhere, right, with the feature values and so on, then that is the condition of satisfaction, that it matches, that what I have in the matches. For perception, it might be considered trivial, but for instance, I have a working memory. Before that, I might have only some feature values in memory, like, I might remember this participant has this green sweater and blue jeans, and just stole maybe green and blue, and maybe not some other details. And then it's a working memory, and then I look back and I might find, not in this case, let's say I misremember the color, right? Or he switched shirt. Then I would have, it's not satisfied, but there is no match. And then something would happen. For instance, that intentional state would be deleted, and I might actually store a new working memory that now with this change. That was not just a genius example, but you can imagine things like that might happen somewhere. So this the same kind of thinking can be applied to the other kinds of intentions. And actually we do work on that, but I'm not lecturing on it today. So I'm only talking about this motor kind of intention. And so to make this logical concept a process concept, what we do is we say, the condition of satisfaction requires some prediction. And I know many of you will like that because that's such a fashionable concept. So it's a notion that when you have an intention, then you can predict, you have learned that and your nervous system knows how to do that, what would be the case when that intention has been realized? Right? Once you lift your arm, then you could say, well, certain sensory neurons here will tell me, the muscle will feel a certain way, and when I look, I will see my hand up there, and a couple of things like that. So here it's a bit trivialized because, to make it simple, we said that what we're predicting is the color, right? I want to have blue, and then I'm predicting I will see something blue. We will, by the way it's wired up, we will make sure it's a certain quality. For instance, it's a large blue thing. Enough, and large will mean here vertically extending a lot along the array. So I have a lot of pixels that are blue that match that color. And so operationally, this is done by having this attentional field providing input into this condition of satisfaction field, input predicting that color. But that input alone is not enough to make a peak. And then there is another input directly from the visual array. And when that input overlaps enough, and here literally overlaps in hue, and the inputs are large enough, then these two can go through detection instability, make a peak. And then what we'll arrange, so once we can detect the condition of satisfaction, what we'll do is now we'll say we're done. And the being done shows up as an inhibition. The inhibition is not directly on this field here, it's on some ordinal machine, which I'll explain a little later, which suppresses all the neurons that store memories. And then when the inhibition goes away, I'll show you later, then the next item can come up here, and the next item can be activated. That's this thing I'll explain later, how you select the next one. Good, so that's the principle. Now let me show you some insights. So the visual search part, this is how you have from the visual array, you get input that is informative about spatial location. So it's just along the horizontal. This would be that direction. And it's about color. So this is color dimension. So hue on the computer can be hue. In the brain, it's a bit different, right? We have these opponency systems. And the strength of the input, we simply took how many pixels in this spatial location are yellow, right? So for instance, for this location, we have a lot of yellow, and that will make that the input is at yellow is quite strong, and the white actually is not counting here because we did a white table that's background. And so there will be only a single peak here. If there was a red object also in this region here, there might be another entry here at red, whatever bimodal entry. So that is a localized input in 2 dimensions, right? At this spatial location, and then along color. And the amplitude is determined this way by how large that is. Yeah. And that that gives you 2D input. Now this is now a space color field, with space being this horizontal direction. And so this localized input, for instance, comes from some object there at a certain orientation that has a certain height. And we'll do visual search by putting a Q into this space as a ridge. The ridge is constant along space because we don't know where the object is, and it is localized in color. So if we're looking for a yellow object, then we would make this peak here at yellow constantly in size. And now you can see with research that is, if these 2 inputs overlap enough, then it can really form a peak. This is not yet a peak. And then we will say we've found the object. And then something happens here. In this case, then the robot starts to steer directly into this direction. Right? This is visual search, as we have seen it before, with just 1-dimensional space. And this just comes from the robot that's walking around there. So that rather than providing stimuli as we do in the lab, here the robot provides its own stimulus by driving around, right? This driving around is very simple. It's just going straight unless there's an obstacle. It has some obstacle sensors, which I don't explain here. And that's the only reason why it sometimes turns. Right? We have these walls, so it doesn't go away. It just always goes back again. Right? So the only way it roams is by avoiding obstacles. You can see in the video, it doesn't do that perfectly. These sensors are pretty awful. They are infrared sensors. So it sometimes runs into an obstacle a little bit, but then it turns. Okay, so that's visual search. And so here is another cut through that. Again, the intention field has a peak at the desired color. That makes this ridge, this is what I just explained, the color space field. The ridge, the camera gives you these localized inputs, these individual spikes. And whenever there is a peak here, you will have the search, you found the object visually, and now it could be, in this scene, it could be one of those, I don't remember which one. And now you're steering in that direction of that. And the steering will make that the object will be in the center. And as you're driving closer, it will get larger and larger and larger, right? Because it's vertically, get closer, comes larger on your retina, and that will ultimately make a larger amplitude of that peak. And that will be, it's actually here, that the amplitude of that peak will be then input into the conditional satisfaction field. So there's an input from the perception field, and the perception field, the thing that you're looking for will be the large one because you're moving toward it. And then the intention gives you another input. So this comes here from the intention. And when these two overlap well and there's enough amplitude, then this makes a peak. This conditional satisfaction thing makes a peak. And so this is a simulation of that. They're all running in parallel. So here's the current intention. Here's the visual search machine, some two input. And this is actually the condition of satisfaction. It's a single neuron here. I'll explain that in a second. So you see here an event happened. And when that event happened, it actually stops the previous behavior, brings in the next one. I haven't explained that yet, how that happens. Now it's looking for something here on this ridge, and there's some inputs here, but none of them. Now suddenly it switched. There must have been some significant peak here. Now it's looking for the next color. There is something here, it's maybe not enough yet. And some moment later, it makes a peak here. And I don't know, switches here. Now this is super threshold and or gets super threshold, and then no, next thing happens. This is the first thing how events happen, right? You see the events is this detection events, conditional satisfaction firing, and then something changes in the system. Huh? So I haven't yet explained how the instability comes about, but this is the peak comes from a detection instability, right? The condition of satisfaction goes through a detection instability that triggers the events. As you can already maybe see, the robot is driving with constant velocity, just turning. Now, and this constant velocity movement leads to these discrete events by the detection instability when its expectation is matched. That's sort of the core idea. We'll lift that idea everywhere. Later we'll say, when you do thinking, then in your mind, some continuous stuff happens, and then suddenly something fires, and you go to the next thing. So I have to explain how do you stop the current attractor? And the simple idea is that when the conditional satisfaction fires, it inhibits the intention. So here what it does, this is a different variant where rather than discrete intention nodes, it has a whole set of fields in which there are under threshold, localized peaks. These are the colors you want to do. They're below threshold, and they all compete. So only one of those fields can be active at a time. And when one of those peaks is detected, then it just inhibits this entire thing. And as it inhibits that, there's no more intention, no more input to this field. So this peak goes away, the reverse detection instability. If this goes away, then the precondition input, this peak goes away. No, sorry, if this peak, what did I say? This was inhibited here, so it's nodes there, it was fields. So if this is inhibited from the conditional satisfaction, this peak goes away. If this peak goes away, one component of input to this here goes away. That puts this peak below detection. And even though you still have the same perceptual input, but now this is no longer, it needs both of these inputs to have the peak. So there's a reverse detection instability here. And as that happens, the inhibition goes away. And now the system is reset, right? So now there's no peak here, no peak there, and this thing, it has no neuron or field active, and it now recovers from inhibition and something new comes up. And in this case, this is wired up so that the next node becomes active. So there is a memory node, sustained activation here. And if you inhibit all of these and then release from inhibition, the one where there's a memory will actually activate the next one. That's how it's arranged. So it's like some chaining kind of idea. But it is, it doesn't know about the colors. Actually, these nodes project onto this color space and then the next color comes up. Well, that's the way it's done in this particular case. That's the core idea. Here's another illustration of this. So here, this is the field in which the condition of satisfaction is represented. So it's along color space. And this is the intention of color. So he's looking, it's for that particular color, it's this intention here, maybe standing for red, I don't remember, has activated that peak. It projects onto that location in the color field. It's like a concept node, we call this more recently, right? Makes this color peak. And it's at this point that see this little input here, this subthreshold input comes from the intention. But there is no match with perception. At this point, there is a match with perception, which is not shown here. And that makes that this peak becomes active. You see now it's a suprathreshold peak. As that peak starts to inhibit everything. As this peak arises, it inhibits this system. This is the ordinal system. That is where the different intentions in their ordinal form are stored. They're all inhibited. As they're inhibited, the intention field falls away until it's totally gone. Oops, sorry. And as the intention field goes away, the condition of satisfaction field goes away because it doesn't get that input anymore from that. Right? So here's gone away. And as this goes away, the inhibition goes away. So this recovers from inhibition. And by the way this is done, the next node is higher than the one that you just did because it has a memory that you just did that inhibits. And so you're activating the next node. And then this node has learned that color and this new intention comes about. You can see it already pre-activates the condition of satisfaction, but that's still below 0. That's a concrete mechanism in this model. So when you look at that together, this is over the entire sequence, then you see that this is the condition of satisfaction. You see these events when this becomes blue, a peak is formed here, so it's the end of a period, and then the new intention is read in, and then an event happens, new intention read in, and so on. And so you can see here that when it produces these events, it does the right order, red, blue, green, blue, the order that it learned, yellow is the last one. But it takes different amounts of time because it's driving around the arena to find the corresponding object, right? So this does the thing that we want. It goes through these states in the serial order that it was taught, but it can it really terminates the state only when it's done, when it gets from the world really the information. I found the object I was looking for, an object of the category I was looking for. In the front part of this, you see the same sequence generation during teaching. So during teaching, the intention comes about by showing the object to the robot, and then when the teacher makes the object large enough, it uses the same condition of satisfaction to switch to the next node. And you see it looks a little bit rhythmic just because the presentation is paced that way, but it would have to do that. This here in the end is just informative of where in the visual array the object was, but that's not important. And so this is a solution to that problem, right? Very general kind of solution. But got that. See, this the reason why we do this so late in the lecture is that this is a architecture that is, where it's integrated, that it's through the interaction of these domains that this happens. It's not one little module that does that. And in this particular case, it's also in closed loop with the outer world, which is something we didn't really study so much now. And in summer semester, I'm talking about autonomous agents and motor behavior. And that's where that happens, right? All motor behavior is actually, in that sense, in closed loop. Except for some pathological limit cases, but pretty much all the time, what you do when you do motor behavior, you change your relation to the environment. You move in the environment, right? And therefore the environment provides the new input. Right? So we're not actually sitting there getting new inputs, but we're generating it ourselves by moving around. And in a sense, even internally we do that, right? You remember this attention selection, you're intending to a particular object. So the neural state that is transmitted for those states is also changed by active choices that you make. So inside these complex architectures, there was something like that, an internal loop, but there's an internal loop. And I'll show you some sequence generation that isn't, actually, I'm not sure I'm showing. I'll refer at least to sequence generation that doesn't require that outer loop. But that's the complication why that's a bit difficult. Good. Just briefly, an abstraction of this. And so this is the general mathematical mechanism for that. So we would say these kinds of intentions, world to mind, have the structure that you have some representation of your current state that we call that now the intentional state, has some dimensions. It can be multiple dimensions, it can be a whole bound, bound across space, can be complex objects. And I want a yellow striped diagonal objects and kind, categorical, and so on. And from that, that intention acts on something downstairs, that is, acts on ultimately maybe on motor behavior. It could also just act on some neural processes. And it predicts the outcome, right, the condition of satisfaction, which pre-activates that representation, but doesn't make a peak. That could be a different dimension, right? We use color as the same dimension, but it could be that you're predicting something entirely different as a consequence of your action. And the effect of the neural or motor action is that you ultimately get some input to this representation. And when that input overlaps along these feature dimensions, goes through the detection instability, makes a peak here, and that inhibits this intention. And when that intention falls away, the prediction falls away, goes through the detection instability, the reverse detection instability, no more inhibited, and no more inhibition. So no more inhibition here, but this was driven, it was in a working memory state essentially, so that then this system is reset. There's no activation here and no activation there, and you're done. And now some other system comes up, and we'll think about that. So in the slides, this just explains what I just said in words, so you can read that later. So essential to this is some form of prediction, right? It's that you can get to the next state only by knowing that you have achieved the previous one, which involves some prediction of what it will feel like when you've done the previous one. And that's maybe familiar to some of you. There's this efference copy idea. Sometimes it's also called reafference. Does anybody know that efference copy? No? So then that is related in this predictive coding. That is a very fashionable idea, and so it's also related to that. It's actually complicated relationship. It's almost the opposite, because in predictive coding, efference copy, you're using the prediction to not transmit what you're currently doing. You're saying, if I can predict it, I'm not going to even use the sense information, because I only transmit stuff that's surprising, that's new over my prediction, which is some predictive coding is used as a way to minimize your sensory dependence on sensory information for compression, which is sort of the opposite of this if you think through that. And I actually think that predictive coding is not the principle that psychologists react to. It's actually the prediction, where you actually pass on the prediction, do something with it, and this would be one form of using the prediction. That is right. So I actually don't think that this is analogous to predictive coding. I'm just establishing some overlap with this idea of prediction, but the role of what you do with the prediction is different. You're not preventing yourself from transmitting that information. This is actually also the way of how efference copy is used. That's why efference copy overlaps with that. Efference copy is the idea that you're not acting on stimuli that are caused by your own action, but you are acting on bending your movement. For instance, the notion that you would, like, you move your eyes, and the movement that is caused by that is not perceived as movement, because it's just because I moved my eye. Good. That, if you don't know that, it's not so important. So we generalize that. So in some of our architectures, it takes more complex forms. So for instance, you could think of the condition of satisfaction is sort of, you're detecting that you're matching your prediction. And you could think that's a more general form of match detection that could also underlie change detection, to say I have something in memory that predicts what I will see when I look back at that location. Then I can detect whether that's actually the case, or I could detect that it's not the case. So we call it the condition of dissatisfaction, which would be the opposite. And in fact, in some cases, it is easier to neurally detect a non-match than to detect a match. Right? For instance, if I have to say same versus different, There is nothing in the stimulus perhaps that tells you that now, the only thing is that you're asking, is it the same? When you turn it on again, is it the same? But if you were to just continuously look at something, there's no signal for same. But you could say, well, my default answer is always to say same unless there is some difference I detect, and then I'm stopping that same. Right? And that is the more general form of doing that. I'm not going into that, it's just point to that fact. So we're using this across the board in a more advanced form. I'm not explaining the detail of that. Okay. So that is the core idea of how we get rid of an attractor in the self-controlled way. So in all of the architectures I showed you, there was a principle like that happening. It wasn't always organized exactly this way. It's organized that there is some detection in some system that then inhibits, that triggers reverse detection. We sometimes talk about it as a cascade of instabilities, where the detection, then reverse detection and reverse detection, but it's mathematically speaking all happening at the same time, right? This is just a mental thing to think of it as a sequence, but it's one mathematical thing, just the way you understand how it comes about. So this is the aspect that all literature models of sequence generation ignore. It's kind of funny, right? When we did this was really new, because they're really ignoring how this is handled in time. All the models in literature deal with how you determine what to do next, but not how you organize that in time. In fact, there are famous connectionist models, so they're also neural in this sense, neurons. Maybe best known is Botvinnik, someone called Botvinnik, who's now very famous at DeepMind. He's sort of not really a major figure at DeepMind. He was a cognitive psychologist, and he had a model that was even somewhat famous back then. Botvinnik and Plaut, I think, I remember, maybe with Plaut, connectionists, old stuff. And that's a model that also is supposed to store serial order, and that's like a transient kind of model. That is, you have one neuron coming on, and then it triggers the next one, and that triggers the next one, and by providing input to that, so they're chained in that way. And you can see that really only works if the timing is right, right? Because it's always clear that the next one has to come up, and then there's the next one, and so you couldn't keep one up longer until something happens. So it would just transiently go like that. So this would be literally a system that would go over to the next section, even though you're not done on the previous one. It took a little bit longer, right? So this is really the aspect that we treated here. And it plays a role in mental operations as well. So I remember I showed you this mental mapping, where we're putting a peak into the mental map, and then we're going to the next thing. And that's, you could think if it's purely mental, like just creating a sequence of events, like in covert attention, because well, it takes a typical time to bring up a peak. And there's a proposal in the literature that there's some kind of clock that every 50 milliseconds, you update your brain state. Just fit some data. And we actually also sometimes postulate something like that. There's an oscillator that does that. But it's not generally true. So even purely mental operations will sometimes take longer to achieve. In this example with the mental map, remember where I'm saying, well, you take a new relation and you have the previous object in your mental map. Now you're putting a new object in the mental map. And that will take longer when there is another object already in the map, in the region. Remember, there was this problem I think it was last week, where when you have already put up, like the Porsche is to the right of the Volkswagen, and then you say the Opel is to the right of the Volkswagen. And so you have to put it outside of the Porsche, for instance. And that came up because in this field with the relations, there were, in this kernel, there was already inhibitory influence from the previous object. So you pushed a little bit outside to put it there. That inhibitory influence will make that it takes a little longer to make that new peak in that case, which matches human performance. It also takes a little bit longer in these cases to make up your mind. In fact, pretty much twice as long in our numerical simulations. And so that is an example of a purely mental event that can take variable amounts of time, depending on how complicated it is, in this case, how much inhibition there is around, how many things you compete with. You could see similar things would happen that if you're not in your mind, you're trying to you decide for, let's say, which concept to use, and there are some competing concepts that are maybe right, and you have to choose between them, then it will take a little longer for you to mentally make your mind up about what concept to activate, for instance, in what word to use. And there will be examples where you're really confronted with this problem of solving the timing code. So that's what we address here. Now, the other question of what state to select next has been a topic of theoretical thinking and both in information processing terms and neural terms for a long time. And there are in the literature 3 notions, and that's been since the 80s, I think, been the consensus, and the current idea is that all 3 occur in the brain. And so there is no real difference with respect. So there's a review article by Henson and Burgess, who did this from the 90s, where that's already mentioned. So there's one is called gradient-based selection, the other is called chaining, and the third is positional representation, which I'll explain. I'll go through all of these 3. We use all 3 notions in our model, so we're not saying only one of those is reasonable. So gradient-based is sort of the notion that you would have activation of different activation levels, different amplitudes, and at some point, which for us would be the result of a condition of satisfaction. For the others, it's sort of controlled from the outside. Somehow now you decide you want to activate the next item, and what you would do is say there's bias competition, that is, you're bringing the system to now make a selection, for instance, by boosting the entire field. And then the one with the most input will be selected. For instance, the most salient object will be activated. And that is actually literally happening in our visual search machine, right? That also does sequentially do things. And the next item is going to be the one with most input. And we were able to organize that in a nice way by having also inhibition of return, that is, having a memory of locations we already looked at. And that memory makes that the peak you previously looked at is now no longer so strong. And therefore, the location where you have no inhibition of return, where you haven't, the way you looked at is a working memory, right? Where that working memory is not inhibiting, but there is some visual input, that's the one that is more likely to activate. And that way you can actually systematically scan the scene. And there's actually empirical evidence for inhibition of return. The way that there's some subtleties about that, or technically speaking, inhibition of return is measured often as a intended attentional shift that is then disrupted by something. And then you can see that you take longer to redirect attention at that previous location. That's evidence for that inhibition. But this form is also consistent with some empirical data. So we're using this already. We're using in other architectures, and this is in a more general sense, that it's always the next most activated. Like, for instance, you have multiple actions to compete because you have some coupling among your actions that say different things you can do. And then when you're done with the previous one, you restart, and then one of those actions will win. And sometimes this can be stochastic, that you have multiple possibilities and you just select one of those. And yeah, so that's how I synthesize that literature. There's actually a little bit more detailed thought in the literature. So there are some people who argue, and Stephen Grossberg is one of those I might have mentioned initially. So he was the first neurodynamicist in a certain sense, and he argued even that you do this systematically, that is, you store in working memory different levels of firing. Now, we said peaks, sustained peaks are working memory, and some people think you can have what they call line attractors, that is, rather than have peaks in different locations, you can have a neuron that can fire different levels, and you can determine, and these levels are the memory. And mathematically, that's possible. You can sort of arrange that the minus u term is canceled. So u dot equals minus u makes it decay. But if you have a plus u, you can cancel that, and you have u dot equals 0. U dot equals 0 means you stay at whatever level of activation you have. It's quite unstable. If you add a little noise, it will drift and so on. But our peaks also will drift. So that's being proposed. So some people who talk about gradient-based mean that you have peaks whose height is ordered, and then you will systematically go down the gradient that way. But I would say gradient-based is a much more general principle, and this is a very specific proposal for which I don't think there is so much support. Okay, so that's gradient-based. Now, I already said that. Now, chaining is the idea that there is some fixed directed connectivity. That is, you have something, for instance, this is from some of the model work, we have some intentions. This will be an intention and its condition of satisfaction, another intention with its condition of satisfaction, a third one. And you could have some directional ordering. We call this here a precondition node. That is, this node, when it's active, inhibits this one. So when this is active, then, and these two get input, then only this one can be activated while this one is inhibited. But as soon as this condition of satisfaction arises, it inhibits that inhibition, now double inhibition, which means this is released from inhibition, and then this one can be activated. Now, this is how one triggers the next in a more attractor-friendly way. And there's actually some neural evidence for double inhibition. Basal ganglia have a structure like that. They inhibit everyone, and then if they are inhibited, then the one they inhibited can be released from inhibition and you do the action. And so we use that in some of our architectures. I didn't go so much into that. And so this is a good model of fixed sequences where where I was saying by grasping, right, where there's a logical constraint that you have learned. Actually, children in childhood need to learn that. They don't get this right initially. And there's a phase where they start to do this right, to open the hand before they are at the object. And so that is often postulated for fixed behaviors like that. You could see as a general mechanism for sequence generation, it's a little bit problematic. For instance, this has a very trivial problem that if you have a sequence that goes through the same state, but with different futures, like you search for a red and then for a blue, and then later you search for a red and you search for a green afterwards, right? So red occurs twice in the sequence. Then that's a problem because you're by chaining, you're arranging that from red, the next one is this one. And it's difficult to handle that there are different futures. They only solve this by is having multiple copies of red. Have red number one, red number two. So, but there is some argument that things like that happen, and these arguments come exactly from bottlenecks like that, where you see that there are certain things are harder than others and so on. That's sort of supported by this kind of idea. And the positional system, the most general one that we used, actually has a chaining element in it, but there's an additional element. So the positional representation is one in which you're saying that you have a representation of order. So you have a fixed, so it would be like a chaining system where you say, this is neuron for the first thing, this is a neuron for the second, that for the third, and you have some directional system that makes that. In general, the activity will go from the first to the second to the third. But now what that first node stands for is being learned, is flexible. Right? That is, you will say, I just learned that the first projects onto some field, that connection is learned, and then the second is learned, and the third is learned. That's actually what we used in a moment ago. That is, when this was trained, what happened is that through Hebbian learning, the system associated with a node, a particular color, and that connection, so it was this connection that was flexible, was from a node that had a fixed position in the serial order machine. So, and actually a lot of our more recent higher cognitive models use that idea. I hinted at that when I talked about grounding, that when you have a syntax tree and you want to ground that, it comes the chair that's next behind the chair that is to the right of the door or something like that, right? You know, there are two different chairs, and you know that the chair in the first relationship that's chair number one in a way, right? Is in a relationship to chair number two, and then chair number two is in a relationship to the door. And the important thing is to know it's the same chair number two I'm referring to. When you have syntax tree, that's the core idea of syntax trees, that you have similar elements, but they're different copies and they are in different relationships. They're called tokens when you talk of of a certain category in the cognitive linguistics. And so there the notion is that you're giving a feature to every object, which is where it is in a ordinal working on these things. So you will say, oh, we call that an index dimension, right? The first instance of category, and then the second and third dimension. And you can generate these indices by having an ordinal machine that, in a sense, keeps counting, right? You have a limited reservoir that is, after 4 or 5 indices, you're out, you're restarting from the beginning, you just forget the old bindings. So this is a very important idea for us now. So that's how it was done there. That's called the positional system. It's considered the most flexible and general system. Is there evidence for that? There are some frontal brain neurons that, after training a monkey, look like that. That is, for instance, there are examples from monkey neurophysiology where in these frontal areas, the monkeys learn to look at colors in the scene in an order. It was first look at the red one, then the green one, or even point. The study I remember is looking, but maybe there's also something. Like you have to point at the red and then the green and the blue. And then you see that some neurons are tuned to a color, but only when it's the second. So only to green when it arises as the second, not when it arises as the third. Right? So they seem to represent a combination of feature and orientation. And that will be consistent with that they learn the link to the feature, but they're also tuned to a particular ordinal position in a sequence. Yeah, of course, always to find neurons like that. Does that mean it's exactly like that? Of course, it's a bit hard to say, but it's not totally out of the question. Good. Yeah, so that's the architecture more completely that we really used in this, or the ultimate architecture that we used in that earlier work, where the ordinal machine up here made the intention, and then that intention drove the motor system, as I was saying, and also makes the prediction, the condition of satisfaction. And then the motor system generates the perception that influences this, with the driving toward the goal, but also the condition of satisfaction perception, which triggers this. And then when the peak arises here, it inhibited this whole system. And when you inhibit these ordinal nodes, everything they project to falls away. That's what I explained before. And this peak goes, and because this input goes, this goes away. So this is all reset. And therefore, this inhibition goes away. And then when the inhibition goes away, this creates a peak again. These nodes compete with each other. And the fact that there is a working memory for what you just last activated, that will bias the selection. So next time this one is, now it's gradient, it's using gradient, right? The chaining is in a sense using gradient. Now the next one comes up and the peak comes up here. So this actually combines chaining, gradient, and positional, but the chaining is fixed, the gradient system is fixed based on this memory thing, and the positional is where the flexibility comes in. And that architecture has turned out to be very scalable. So we use this now in our cognitive linguistics work, for instance, quite reliably. So there are things which we were going to do this. You can build things like that in CEDA quite easily. We'll do this in the summer school. Anyone who wants to deepen in that can go to our summer school in August. I think it's August, and we'll take local participants. We used to not do that, but this year we wanted to do that. It's on the dynamicofieldtheory.org, where all the simulators are. There's a pointer to that in the summer school, and you can apply if you want. But it overlaps a lot with this core, so you might want to go there if you really want to learn how to program these things. Yeah, so I already said that there's actually some story. Hippocampus might be connected to that. There are some issues. So hippocampus has neurons that from single, so good candidate for these connections. And there is something in hippocampus. Anybody knows about hippocampus here? There's, it's often linked to spatial navigation. And spatial navigation is sort of the ancient memory task. I mentioned that earlier. And the actual representation used is like a graph of knowing certain discrete points where you go, like in a labyrinth, at this crossing you have to go left, and that crossing you have to go right, stuff like that. And there is something called replay. So you have neuron signatures of what neurons in hippocampus are associated with, which, for instance, which place in the labyrinth they're associated with. And after an animal has learned to navigate in that maze, they will the neurons that are associated with some place will show up in the order of going through the labyrinth, right? There's a natural serial order in navigation, because when you go through a labyrinth and in the real world, go on your little graph network, there's some topology, right? You to go to this one, you have to first go through that one, right? So there will be a natural serial order in which to experience the different places. And so people say, well, when you do a replay while you're sleeping, it's just mentally going through the same sequence. But there is also something called pre-play, where you sometimes see mice that before they have learned the labyrinth, you already see certain regular sequences in the neural patterns. And then once they have learned, that's the sequences that are through place fields associated with a path through the world. So how come that these neurons already can activate in the sequence? And the idea would be they are wired up in some way. This is, of course, just a very macroscopic picture of that they are sequentially activated. And the thing that they learn is just how they map onto place, how to learn the place fields. So that's a potential connection. Because this is a model just in our dynamic field theory sense. We're not really thinking exactly how that's done in hippocampus, just that there are places in the brain that look somewhat like that. Yeah, so last story I want to say is just an example. So I'll show you these architectures that I already showed you last couple of times. This is one example that we published a few years ago that combines a lot of the things we did. So it's about a robot that looks at the table through a camera, and we show the robot some objects of colors in a particular serial order, and then we present to the robot that whole set of things, and we ask the robot to point at every object in the sense of moving its hand here on top. So it's sort of like the Julius and Emiskaya system with a vehicle, but in a more visual cognition kind of setting, where it's a scene that you're looking at and you're acting on that scene. And the architecture behind that has these three components. This is essentially the visual search machine that we looked at earlier. We have this visual array, you have a color that you're looking for, and then that color makes the slice input, and that slice input biases you to select an object that has the right color, right? And which color you're looking for comes from a serial order machine, as we call that, this sort of thing that we just discussed. And that's in that serial order machine, the individual objects have learned the connection to the color, in the way I just hinted with the Hebbian learning. And then when an object has been found, and I'm in a particular sequence, then it will generate a movement. And this is a movement architecture. This is something I didn't really explain in a lot of detail. I do that more in the summer semester, where there is actually a real neural timer somewhere. Actually, what you have to do is you have to transform the coordinates of the object into the initial position of your hand. Then you know the direction, how to move. And then you make a time signal and move the thing there, and you have to finish, move conditional satisfaction when you're done. And then you tell that system to do the next step. So you're not just, the next step is not just having seen the object, it's also actually having achieved that movement. And that works. No, that's all it does. In fact, this has interesting features. Here is maybe the high point of that. So here, for instance, the system has these three in memory. Currently, it's queued. The first index is green. It goes to the green object. It will be this one. See, this is its target position. It will ultimately move there. And then it activates the next one, which would be here, this, I think it's blue, this blue object. Oh, sorry, I meant this slide. This is the same, but as it has focused on the blue, we're actually making the blue object jump. See, it's has the peak where the blue used to be. And as it is going, it will make the object jump to a new location, and then it has to update its target. That's sort of how we show that it's not like have a fixed program. You took the scene in, now you make a program making these movements. It's actually able to, any time, to link its intentions to online sensory input, right? So it's much more powerful than like storing fixed action patterns that you somehow learned, right? So it can still reach that new target here. Still, it's all in simulation. We didn't do this. We actually own that robot. There's really not so much gained by making the robot. We did this, sometimes takes forever, you know, have to make sure that it doesn't crash the robot. Computers often gives you a fallout and so on. So we do this more often now in simulation. Good. That just summarizes that. So now maybe some of the things that you saw in this previous simulation, you know, hypothesis testing, remember the sequences coming up. Inside that is that principle in many different places that are not so easy always to see from the outside. They actually combine all of these techniques. They are chaining ideas because, for instance, there is an idea that you would have to first direct visual attention to something before you then, for instance, establish a relationship, right? This grounding, you have to have the reference object before you can look what is to the right of it. So that will be done by some chaining. And then I hinted at how positional is important for this index assignment. And the gradient, you know, is based on the, you know, salient space selection, for instance, of the most viable object. So this principle of the conditional satisfaction is something useful to really try to understand. So if you can sort of understand that principle, that would be useful. Other than that, this goes, of course, beyond that sort of stuff that you can really know in an exam. Good. I'll stop the recording.